Hello everyone, so in this video we would be discussing about how we would be solving the product of inertia of a certain section. So as per the definition here, the product of inertia for an area is the summation of the product. So you would be multiplying the differential area by its moment arms about the two perpendicular reference axis. So in this example right here, if this is to be your reference axis and this is to be your figure or your section, its differential area is to be multiplied by this its respective x and y lever arms. And since we are to talk about differential area here, our general equation for the product of inertia would be the summation or the integral. So by the way guys, your integral symbol is actually an elongated S, which indicates summation. So it would be the summation of your x and y lever arms times the differential area. So this is to be our general equation for the product of inertia. So okay, and its units would be in terms of millimeters raised to fourth, centimeter raised to fourth, meters raised to fourth. So it would be depending upon the customary unit or the unit that you would be using, as long as it would be raised to 4. So there. And it is stated here at the bottom part that the sign of the product of inertia depends on the location of the area relative to the axis. Relative to the axis. Because in product of inertia, you would be considering your sign convention, which is for x, for the x component, to the right positive, to the left negative, and for the y-axis, that is to be upwards positive and downwards negative. Then as you can see here, you would be multiplying them. So x times y. So for example, that the geometry that you are referring to is in this area right here. So if if this one right here, if your figure is to be in this quadrant right here, your x component would be positive and your y component would be positive. So positive times positive would give you a positive answer. And for example, that your geometry is to be located in this quadrant right here, its x component would be negative and its y component would be positive. Thus, it would give you a negative answer, since positive times negative is to be negative. So negative. And for example, that your x-axis, your x component is to be negative, and your y component is also to be negative. So to the left and downwards, so multiplying both of this, it would give you an answer that is positive. And if, for example, that your geometry is to be located in this part right here, and let's say that your x component is to be positive, so it would be in the right. And if your y component would be negative, which is downwards, so positive times negative would give you a negative answer. So it would be as simple as that. But take note on this note right here that it is said here that the product of inertia is 0 with respect to the axis of symmetry. So what is an axis of symmetry? So for example, that we have this, both of the symmetrical members right here, and your axis of symmetry is the axis that would divide your geometry into two symmetrical figures. So this one right here is to be your axis of symmetry, and this one right here is to be your axis of symmetry. If those axes would divide your figure into two symmetrical figures. So if this is to be your axis of symmetry, this area right here should be symmetrical to this area right here. And if this is to be your axis of symmetry, this area right here is to be symmetrical to this area right here. So similarly with this I section right here, if this is to be your axis of symmetry, this area right here on the left should be symmetrical to this area right here on the right. And if this is to be your axis of symmetry, this area right here on the top should be equal to this area right here at the bottom. So those would be your axis of symmetry. So if once again we would be going back here, so once again it is said that the product of inertia is 0 with respect to the axis of symmetry. So if this is to be your axis of symmetry, your product of inertia is to be 0 in that axis right there. And by the way guys, it is said here, so I would just be moving this first. So it is said in this part right here that it is denoted by the symbol pxy, wherein the subscripts denote the reference axis. So once again, that is to be pxy. And this symbol right here would depend upon the book that you are using. And in my case, I am using the book by Ferdinand Singer, which is Engineering Mechanics, Statics, and Dynamics, which is to be this book right here. But if you would be looking at other books, they would say that the product of inertia is denoted by IXY. So they are practically the same. So it just depended on the author that wrote the book. So once again, this is also equal to IXY, and it would depend upon the book that you are reading. So our general formula once again is to be the integral of x, y times the differential area. Okay, so considering this, just to prove this point right here at the bottom that the product of inertia about this axis of symmetry is equal to 0. So as you can see here, if you are to get the product of inertia about this point right here, and as you can see here, this area right here is also equal to this area right here, and this area right here, and this area right here. So all of them are equal. Not just the area, but also the geometry and the shape properties. So meaning, the product of inertia at this point is, let's say that this is to be P, and this should also be P, and this should also be P, so PXY, 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 and PXY. So all of them should be equal. But take note, guys, that considering the sign conventions right here, so in this, in this quadrant right here, your x is to be positive and your y is to be positive. Thus, your answer here would be positive, your answer here would be negative, your answer here would be positive, and your answer here would be negative. And if you would be getting the summation of all of those, so positive pxy minus pxy plus pxy minus pxy, which are all of these terms right here, this would just give you an answer of 0. So that is just to prove here that the product of inertia is 0 with respect to the axis of symmetry. So with this being said, if you would be having this section right here, which is, let's say, a square, a rectangle, as long as it is symmetrical, your product of inertia is always equal to 0. So as well as this one right here. So as you can see, it is symmetrical to both axes, and your inertia here is also equal to the inertia here. The product of inertias in those respective sections, and the product of inertia of this section here is also equal to the product of inertia of this section here. And if you would be getting its summation, you would just arrive at an answer of 0. So it would be as simple as that. So once again, if you would be having a symmetrical section, its product of inertia is always equal to 0. But what if that we would be having a certain section wherein it is not symmetric to the axis? So just like in this right triangle right here, if this is to be your centroidal axis, with that being said, this is to be your centroid, the product of inertia wouldn't be 0. So if you would be applying this formula right here, which is, well, pxy or ixy, let's indicate here bar. So this bar right here indicates that this is the product of inertia about the centroidal axis. So once again, let's put a bar here. So if we would be applying this general equation right here, which is the integral of xy dA, so simplifying this equation would give you a result of this equation right here. So for a right triangle, by the way, instead of using this, you can use this formula instead, wherein the product of inertia of a right triangle is to be equal to negative b squared h squared divided by 72. So take note, it should be negative. But once again, this answer right here would just give you the product of inertia about your centroid, which is this one right here. But what if that the axis that you want to solve for is to be this one right here? So for example, that you want to solve for the product of inertia about this point right here. So this is to be the axis that you would be considering. This is to be your x-axis and this is to be your y-axis. So if you would be using this formula right here, you can just directly solve for the product of inertia of this point right here. On this point right here. But is there a way for you to use this formula instead and transfer it here, similarly with the moment of inertia wherein we would be having a transfer formula? So the short answer to that is yes, we do have a transfer formula for the product of inertia. And similarly, what we would be doing is that we would be getting the centroidal product of inertia. Then we would be adding the transfer formula. And if you can remember, in the moment of inertia, your transfer formula is to be AD squared. So this is for the moment of inertia. So I plus AD squared. But in product of inertia, that is to be your product of inertia of the centroidal axis. So in this case right here, it would be this one right here. And you would be adding your transfer formula, which is the area of this certain figure right here, which is, well, the area of the triangle times x and y, which is this one right here. Just take note on the sign convention if it is towards the right and upward, so it meaning it would be in the first quadrant and etc. So that is to be for our transfer formula. So for this section right here, which is this square part right here, or this symmetrical part right here, so once again, it's centroidal moment of inertia is equal to 0 since this is to be symmetrical. But for example, that you want to solve for the product of inertia about this axis right here, I should say. So this point right here, you would just be transferring this product of inertia to this point right here. So it would be as simple as that. So using this equation right here, so that is to be pxy is equal to the centroidal plus area times bar x and bar y. And our bar x and bar y respectively would be equal to, so writing this one right here, this is to be your x component, which is negative, and this is to be your y, which is negative y. So, and by the way, this area right here should be the area of the hole. So that is how you would be using your transfer formula.